This is question 4 from the 2008 Mmpc round 2. So it says we're going to have theta as an angle between 0 and pi over 2, and we want to prove the following ugly looking trigonometric inequality. So yeah, sine squared theta over 2 plus 2 over cosine squared theta to the 1/4 power plus something that looks similar except for the sine and cosine are in reverse place, also to the 1/4 power, is bigger than 68 to the 1/4. So not only do we have to prove it, but we have to find the theta that gives the equality. I think that the fact that they ask this actually gives you a little bit of a hint, because when you start to think about where is the theta that gives equality, I don't know, maybe you're tempted to just guess and check, and that'll end up working. So when you think about the fact that this expression is symmetric in sine and cosine, and that sine and cosine are kind of symmetric to each other on the interval 0 to pi over 2, you can guess that the answer should be right at the midpoint, and that'll turn out to be correct. So let's do this part B first. I guess before we do that, I just want to say, like, this number looks a little bit bizarre, but let's think about if it's plausible first. So first of all, we know that both sine and cosine are between 0 and 1. So no matter what, this term is at least 2. And same thing for this guy. And so no matter, so like an easy bound would be to say that this expression is bigger than 2 to the 1/4 plus 2 to the 1/4. And so that's 2 times 2 to the 1/4. Now 68, seemingly random number, but it's a little bit bigger than 64. 64 itself is 4 times 2 to the 4th. Okay, so anyway, seems a little bit related. Let's see what happens. So at the midpoint, so I guess I'll say guess, theta is pi over 4. And in this case, sine theta is root 2 over 2. So sine squared theta equals cosine squared theta equals 1/2. And so the left-hand side of the inequality is just going to be 1/2 over 2 is 1/4, plus 2 over 1/2 is 4. And then it'll be the same thing again, right? 1/4 plus 4 to the 1/4 power. So this is going to equal 2 times 4 1/4 to the 1/4 power. And if I think about this 2 as 2 to the 4th to the 1/4 power, right? 2 to the 4th is 16. So I can multiply inside here. So 16 times 4 is 64, and 16 divided by 4 is 4. So we got at least one case that gives equality. We haven't proved it's the only one. So far, for all we know, well, I mean, it's clear that this isn't constant on the entire region. And starting to think about that will give us the idea for how to prove that this is actually the minimum value. All right. So forget about the 1/4 power for now. Just focus on this term. Let me call this f of theta. And the way we can look at this is, as we approach pi over 2, this cosine is going to approach 0, and so we're going to have a vertical asymptote here. So it's kind of easy to believe that graph of f looks something like this. And then because cosine is sine of pi over 2 minus theta. Right? We can say that this guy is just f of pi over 2 minus theta. So that means that the graph of f, the graph of the first part and the graph of the second part are just mirror images. So it's very tempting to just look at this very rough sketch of the graph of the inside function and say, yeah, if I graphically add these guys together, clearly my minimum is going to happen right here. And I can appeal to the graph being easy, but I'm afraid of this 1/4 power messing everything up. So this kind of loose argument isn't going to work all that well. We have to be more careful. And I actually thought about this problem quite a bit, and I couldn't come up with a good trigonometry-based solution. But I know you're not supposed to use calculus on the MMPC, but I'll take you through a complicated calculus solution just for the sake of showing you a detailed calc proof. I'm sure this isn't the best proof out there, but if you want to bear with me and watch it, here's one way we can argue. Okay, so the trigonometry functions are a little bit complicated, so one thing that we want to do is realize that sine and cosine are going to be somewhere between 0 and 1, and if we make this kind of transformation, like cosine squared theta equals x, then because sine squared plus cosine squared is 1, sine squared theta is going to be just 1 minus x. Okay, and then f of x instead of f of theta, f of x is just going to be 1 minus x over 2 plus 2 over x. So it's going to be a little bit easier to deal with this rational function instead of a trig function. So now f of x, I guess because I flipped the order, so now this function has a vertical asymptote at 0, but it's a lot easier to see that this function is going to be decreasing but concave up on the entire interval 0 to 1. And again, f of 1 minus x is going to look like this. But we don't need to, we're worried about the fourth root of this guy. But it's going to be hard to talk about all of this in full algebraic detail. So what we're going to do is give a sort of general calculus argument for this idea first, and then we're going to show some direct computations about this function second. So I wrote these down on the sideboard. Okay, so generic function y of x is decreasing and concave up on the interval 0, 1. The claim is that y of x plus y of 1 minus x has a minimum at x equals 1/2. If we can prove this, and then if we can prove that our weird function to the 1/4 power is decreasing and concave up, then we'll have solved the question. So how do we prove it? Well, so again, it's hard to graphically add, and even when you're just looking at the picture, you can't just say, look at the picture, that's my proof. So let's consider what happens at some other point. So y of 1/2 minus c plus y of 1/2 plus c ought to be, I guess that should mean, yeah, well, we want this to be bigger than 2y1/2. If it happens to be less, then what's going to happen? We're going to search for a contradiction. Rearrange the expression, subtract one of these terms to the left-hand side, subtract this term to the right-hand side, divide the whole thing by c. I should have said 0 is less than c is less than 1/2, just to make sure we don't have a minus sign mistake. Now when you look at something like this, this is the average rate of change of my function on this interval, and this is the average rate of change on the next interval. And so we're going to use MVT. So MVT implies that this average rate of change equals the instantaneous rate of change at some point in the interval, 1/2 minus c up to 1/2. And same thing, but for the interval from 1/2 to 1/2 plus c for this guy. So I'll call those 2 points c minus and c plus. And the point is that if this inequality is true, then the derivative at c minus is less than c plus. But now we can use MVT again on the second derivative, and that would imply that the second derivative is negative for some point in the small interval c minus to c plus. But the function was supposed to be concave up everywhere, so this can't happen, so that's a contradiction. So we've proved the calculus claim of decreasing concave up functions when you add their symmetric image, the minimum happens right at the midpoint. Now we need to prove that even when we take the fourth power, our crazy trig function is still concave up everywhere. Okay, so I hope the writing isn't too small to see, but we're going to let f of x be same as before. F of x is 1 minus x over 2 plus 2 over x. We're on the domain 0 to 1. Now we can calculate a few things. We can calculate the derivatives, f prime, f double prime. And now we're not worried about f, we're actually worried about the fourth root of f. So let me say y to the fourth power is f. And I should mention that we're looking for the positive y, so y is greater than 0. So we want to find that, so it's easy to look at this and see that the first derivative of f is negative and that the second derivative of f is positive on our domain. If we start taking derivatives to find the derivatives for y, okay, I'll use implicit derivative, so I can find y prime, f prime over 4y cubed, and from here it's clear that y prime is always negative. And then I can take a second derivative, and I used quotient rule and I did some simplification on scratch paper. And this is how you can present your answer on Mmpc also, although I don't know if they give full credit to calculus-based solution. But anyway, this is y prime. Now we want y prime to be positive, but that's not obvious just from looking at it because I've got this minus sign here, and f prime and y prime are both negative, so this term is negative. So in order to prove that the second derivative of y is positive, I need at least 4y to the fourth is always positive, but I need the numerator to be positive also. Luckily, I know enough about this function, I can just directly compute this. So this term is positive. I'll algebraically rearrange it. I'll substitute y prime in terms of just f prime and y. And now I'll notice if I multiply by y cubed, I can get rid of all my y's. I can write y to the fourth power just as f. So now I've got something just in terms of f. And actually, let's just compute this directly. I'll write down all of these f functions just in terms of x. So now I've just got an algebraic inequality with x. X is a number between 0 and 1. Because x is positive, I can simplify this by multiplying through by x to the fourth. So again, I skipped some algebra, but I rearranged this inequality so it looks like just a quadratic inequality. So this is a downwards facing parabola, but I only need the inequality to hold from 0 to 1. It's clear that the minimum value of this parabolic function is going to happen at x equals 1 and equals 51. And so there you have it. So that 51 is bigger than 0, so all of these statements are true, and y double prime is positive, and therefore I can use my theorem on the sideboard, and I can conclude that, yeah, my original hunch, my original picture is true. Those two crazy trig functions raised to the fourth power, they're still just symmetric concave functions, and when you add them together, you get a unique minimum at the midpoint, which is pi over 4. And I really want to know the purely trig way to solve this. I thought about it a little bit. Let me know if you find out.